Real numbers, composed of rational and irrational numbers, correspond one-to-one with the points on a number line. Real numbers are one-dimensional numbers. Numbers with imaginary parts added to these real numbers are called complex numbers, which are expressed on the complex plane, where two perpendicular lines intersect. Complex numbers are two-dimensional numbers. The number system can open up new worlds through dimensional expansion. The number system known as quaternion is four-dimensional. Then, what is the three-dimensional numbers? Let's math travel. There was a mathematician who pondered over the three-dimensional number system. That was William Hamilton. Here is the complex plane. This is the real axis, and this is the imaginary axis. Suppose the real number 1 is on the complex plane. Multiplying this number by I makes it I. Multiplying by I again makes it I squared, which is minus 1. Multiplying by I once more gives minus I. And multiplying by I one more time results in minus I squared, which is 1. Eventually, it returns to its original position. Every time you multiply by I, the number rotates 90 degrees counterclockwise. The same rotation applies to other complex numbers. Repeatedly multiplying 3 plus I by I moves it as follows: from 3 plus I to minus 1 plus 3I, to minus 3 minus I, to 1 minus 3I, and finally back to 3 plus I. Each time you multiply by I, the number rotates 90 degrees. Let us generalize this. To rotate a complex number by an arbitrary angle theta, simply multiply by this. If theta is 90 degrees, this becomes I. Hamilton noted that complex numbers were highly useful for rotational transformations in the plane. Then he began to examine whether this concept could be extended to 3 dimensions. He proposed the following form of a number: x plus yi plus zj. Here, x, y, and z are real numbers. I and j are imaginary units. The squares of I and j are both minus 1, but I and j are distinct units. Hamilton examined whether this number system was possible. He checked whether the associative property of addition and multiplication held, as with real and complex numbers. Here are I, and j belonging to the three-dimensional number system. First, let us examine the associative property of addition. We check whether the following equation holds. The left-hand side is 2i plus j. The right-hand side is also 2i plus j. The associative property of addition holds. Now, let us examine multiplication. We check whether the following equation holds. Calculating the left-hand side gives minus j. To calculate the right-hand side, we need to define I times j. If this product exists within the three-dimensional number system, it would be expressed like this. X, y, and z are real numbers. By substituting this and expanding, we derive the following conditions. Ij appeared again, so substitute this again. We get this expression. If the associative property of multiplication holds, the left-hand side and right-hand side must be equal. Thus, this value and this value must be 0, and this value must be minus 1. However, x, y, z are real numbers. When squared, real numbers are greater than or equal to 0. Thus, z squared couldn't be minus 1. Z squared equals minus 1 is a contradiction. The product of I and j cannot be expressed within the three-dimensional number system. As a result, the associative property of multiplication cannot hold. Thus, it is impossible to define a meaningful three-dimensional number system. Hamilton, realizing the impossibility of a three-dimensional number system, turned to studying four-dimensional numbers. After years of research, he discovered that a four-dimensional number system was possible. It was when he was walking on a bridge in 1843. The story of him carving the revelation into the bridge with a knife became a legendary history of mathematics. The resulting system is known as the quaternion. Quaternions are expressed as this: I, J, K are all units satisfying this condition, but each unit is distinct. In particular, Ij is defined as K, enabling the associative property of multiplication to hold. However, quaternions do not satisfy the commutative property of multiplication. Ij is not Ji, but rather minus Ji. By accepting this limitation, the number system could be extended to 4 dimensions. Mathematics has invented the new number system like that. The journey continues.